So the warm-up problems for section 2.5 all have something in common, which is the idea that you have some certain number of objects and you're trying to divide them up in some way. We'll go over 1 and 2a together, 2b and this is 3. 3, those will be covered in the solutions posted on Blackboard. So let's talk about number 1. We have 8 kids standing in a row and each is holding onto a long rope. You need to cut that rope into 4 smaller pieces so that each part of the rope still has at least one kid holding it. How can you do this? So I'm going to start off by drawing a picture of this to try to get a sense of what's going on. I'm going to use little dots here or circles to represent the 8 children. So you got 8 kids in a row and they're holding a rope. So I'm just going to draw this line in between them to represent the rope. It comes off over here a little bit and no one else is holding it. Here, 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 and here. Okay, so here's our children. The circles are our children and this line connecting them is a rope. Now we need to cut this rope into 4 smaller pieces in some way. It doesn't have to be evenly, it just has to be in some way. And we want 4 pieces in the end, which means we're gonna have to cut it 3 times, right? If we cut it 3 times, say here, here, and here, we'd have this piece, 1, 2, 3, and then 4 the rest of it. Right, but that's not the only 3 places that you could cut the rope. You could, for instance, cut it maybe here, here, and here. Okay, that would cut it into 1, 2, 3, 4 pieces. Or, I mean, you could really cut it anywhere. You just need to make sure that at least one kid is holding each piece. So you couldn't, for instance, make 2 cuts between these 2 children because then that would leave you with a little piece of rope in the middle with nobody holding it. And similarly, you couldn't cut it at the end here because that last piece would be falling off. Nobody would be holding it there either. So if we want to figure out the number of ways that you could cut the rope exactly 3 times, well, we need to make 3 choices here. We need to choose 3 places to cut it. And how many options do we have to choose from? Well, you could cut it here, or you could cut it here, or you could cut it here, right? Any space between 2 children, that's where you could potentially cut the rope. So that's 1, 2, 3, 4, 5, 6, 7 spots where you could cut the rope. And you need to choose 3 of them. How many ways can you do that? Well, that's just 7, choose 3. Right, so for part 1, or for question 1, the answer is 7, choose 3. If you want, you can rewrite that in factorials, but you don't really have to. Okay, now number 2 seems a little bit different at first. We have 20 identical pieces of candy, and we're gonna divide them between 3 children, Abby, Ben, and Kara. The question is, how many ways could you divide it, provided that each child has to get at least 1 piece of candy, but they don't all have to get the same amount. In fact, they couldn't all get the same amount. 20 is not divisible by 3. And we want to consider the fact that, in a sense, the order here matters, in that if you give Abby 10, Ben 5, and Kara 5, that's different from if Ben gets 10 and Abby and Kara get 5, right? So the order that you're giving it out matters. These are different children, so it certainly matters to them. So at first, maybe you might want to try to actually list out all the different ways, but you'll soon find that that's very tedious. There's no good way to do that quickly. So maybe your next move would be to try to simplify this and say, what if I only had 3 pieces of candy, or 4, or 5, or 6? That's a good way to go about it. What I'm actually going to do for number 2, though, is I'm going to try to answer this in the same general method that I did here. Right, so this time we have 20 pieces of candy, so I'm going to visualize that. This is 2A. I'm going to visualize that as 20 little circles here. Okay, I don't actually want to list them all, but there's 20 of them, right? These are my pieces of candy, and they're all identical. And we're trying to divide them up amongst 3 children. Well, we can think about that by sort of saying, let's put down a dividing line to represent where Abby's candy gets cut off, right? Abby needs to get at least 1 piece of candy, so if we put a dividing line here, that means Abby gets exactly 1. If we put a line here, Abby gets 2. If we put a line here, Abby gets 3, etc. So let's say we wanted to give Abby 3 pieces. We'd put our first dividing line here. And let's say we only wanted Ben to get 2 pieces. Okay, so the middle part is Ben, so let's say 1, 2 pieces and put another dividing line here. And then Kara gets the rest. Kara gets the remaining, this would be 15 pieces. Okay, so essentially what we're doing is we're looking at these 20 20 circles lined up, and we're choosing just 2 dividers. So we're going to place 2 dividers, which will split up the candy into 3 groups. The first group, so whatever's to the left of the first divider, is the candy that Abby receives. The second group between the 2 dividers is the candy that Ben receives. And the third group, whatever comes after the second divider, is what Kara receives. And so this starts to look exactly like that problem we had in number 1, where we need to choose 2 spots to place a divider. And just like before, we can't put a divider at the very beginning because that would mean Abby gets no candy. And we can't put 2 dividing lines between a piece of candy because that would mean, for example, if we cut out this divider and put 2 here, that would mean that Ben got 0 pieces of candy. It would mean Abby got all this, Ben got nothing, and Kara got the rest. So that doesn't work either. So it's the same rules. We're replacing 2 dividers, and every divider has to go in between 2 pieces of candy. So we just need to count how many places could you place the divider. Well, you could put it between the first 2, or between 2 and 3, or between 3 and 4, between 4 and 5. 1, 2, 3, 4. So you count out all the spaces, and in the end, there's a total of 19 spaces where you could place the candy. Or I'm sorry, where you could place the dividing lines. And you're only going to place 2 dividing lines. And so there's 19, choose 2 ways to place those dividing lines. Now part B is a little bit more complicated because in part B of this question they say, what if not all the kids need to get candy? What if Abby could get nothing or Ben could get nothing? And you can try to use a similar method, but it's a little bit more complicated, and I'll leave that in the solutions for you to read through. Okay, but what these problems have in common is these are all examples of compositions. So this is different from a composition of functions, for instance. This is a composition of a natural number n. A composition is just some ordered list of natural numbers that add up to n. Right? So if your ordered list is x1 plus x2 plus all the way up to xk, and it adds up to n, well, first of all, k has to be less than or equal to n. And in that case, we say that this is a composition of n into k parts. So we write C of n comma k to represent the total number of compositions of n into k parts. And we say C of n is just the total number of compositions of n into any number of parts. So let's try to think about how we could describe those first 2 warm-up problems as composition problems. So in this one we had 8 kids holding a rope. And we needed to cut that rope into 4 pieces, right? But in the end, what that left us with was something like 5, 6, 7, 8. So this was our picture. And if we decided to cut the rope, say here and here, we really divided up the children here. We have 2 children on the first piece of rope, and then 1, 2, 3, 4, 5 on the second piece of rope, and then 1 at the end. So this is a composition. This is an ordered list of numbers that add up to our total number of kids, which is 8. So this is giving you one example of a composition of 8 into 3 parts. Oops, I'm sorry. We're cutting it into 4. Oh, I messed this up a little bit. We're cutting it into 4 pieces, not 3 pieces. So, let's change this a little bit. We need to add a third divider, which means this would be more like 2 plus 4 plus 1 plus 1. So this is a composition of 8 into 4 parts. Okay, sorry about that. And we found in this problem that the total possible number of ways to do this was 7, choose 3. So this is going to represent the total number of compositions of 8 into 4 parts. Now for number 2, we had 20 pieces of candy divided between 3 children. So for example, you could give Abby 7 pieces of candy, and you could give Ben 5 pieces of candy, and Kara 8 pieces of candy. And so we're taking 20 and we're dividing it up into 3 parts. So this is an example of a composition of 20 into 3 parts. And we found that the total number of such compositions of 20 into 3 parts was 19 choose 2. Because if we lined up those 20 pieces of candy, there were 19 spaces in between the candy, and we need to choose 2 places to put dividing lines. So this might already give you some sort of a conjecture at what the formula might be for the number of compositions of n into k parts. But before we actually go and do that, let's do just a couple more examples here. So we're going to try to figure out the number of compositions of n into 2 parts for various values of n. All right, so what we're saying here is take whatever this larger number n is, how many ways can you break it up into 2 parts? And the order does matter in a composition. So for 2, well, there's only one composition here, right? 1 plus 1 is the only composition. It's the only way to break up 2 into 2 parts. So we have c of 2 comma 2 is equal to 1. For 3, now we have some more choices because we could add 2 plus 1 or we could add 1 plus 2. But that's the only way to split it up into 2 parts. So we would say c of 3 comma 2 is equal to 2. When n is equal to 4, we can either have 3 plus 1 or 2 plus 2 or 1 plus 3. So there's a total of 3 compositions of 4 into 2 parts. And when n is equal to 5, we could split it up as 4 plus 1, 3 plus 2, 2 plus 3, or 1 plus 4. So the number of compositions of 5 into 2 parts is 4. There's a very clear pattern happening here, right? A good guess would be that the number of compositions of n into 2 parts would just be whatever your n value is minus 1, unless n's too small, right? If n is equal to 1, then there's not going to be any. I guess that technically works too. So why is this true in general? Why is this our formula for the number of compositions of n into 2 parts? Well, if we look at our examples, it kind of makes sense, right? If I'm trying to look at all the different compositions of 5 into 2 parts, the largest any single part would be 4, because if it was 5, then there's no other part. That's just a composition with a single part. So your first part could be 4, or it could be any natural number less than 4. It could be 4, 3, 2, or 1. That automatically determines what the second part would be. And so in general, the compositions of n into 2 parts would be n minus 1 plus 1, or n minus 2 plus 2, n minus 3 plus 3, all the way down the line, right? And so in total, you're going to end up with n minus 1 compositions. Now, this gets harder to do looking for patterns if you look at C of nk. And so before we actually go over the formula for C of nk, I want you to try the exercise number 2 on the back of section 2.5 problem set. So try that first, and then you can come back and watch the next video.